Why power factor drops when harmonics and distortion are present? Welcome everyone. Today we are diving into a critical concept in power quality analysis. Why power factor drops when harmonics and distortion are present? We are going to move beyond basic linear theory and explore how true power factor is calculated in the modern electrical environment. The power factor basics. Let's establish our baseline. In a standard linear system, power factor is simply the ratio of real power, the kilowatts actually doing the work, to the apparent power, or kVA, supplied to the circuit. Our goal is always unity power factor, where voltage and current are perfectly synchronized, ensuring maximum efficiency. The enemy, harmonic distortion. However, modern facilities are rarely linear. We use VFDs, LED drivers, and rectifiers. These nonlinear loads draw current in abrupt pulses rather than smooth sine waves. These pulses introduce frequencies that are multiples of the fundamental 60 Hz. This is harmonic distortion. It increases the RMS current flowing through your system without contributing any useful work to the load. Displacement versus distortion. This forces us to distinguish between two types of power factor. First, there is displacement power factor, which is the traditional phase shift caused by inductive loads like motors. Second, and increasingly important, is the distortion factor. This metric accounts for the shape change of the waveform itself caused by those harmonic currents. The true power factor formula. This brings us to the math. As you can see in the formula here, true power factor is the product of the displacement power factor and the distortion factor. The equation is unforgiving, as total harmonic distortion, or THD, increases, the denominator grows. This causes the distortion factor to drop below 1.0, mathematically dragging your true power factor down with it. Harmonics bloat apparent power. Let's visualize the impact. In this comparison, notice that the real power, the 100 kilowatts doing the work, remains constant. However, look at the kVA bar. With 30% THD, the apparent power bloats significantly. That extra kVA is essentially wasted capacity that your infrastructure is forced to carry, even though it isn't performing any work. Distortion factor degradation. Here we see the trend line. This chart plots the distortion factor against rising THD. As harmonic distortion increases towards the right, the distortion factor plummets. This demonstrates why you can correct your phase angle perfectly to unity, yet still suffer from a poor overall power factor if you ignore the harmonics. Infrastructure impact. The consequences in the field are tangible. This excess RMS current generates significant heat in transformers and neutral conductors, risking equipment failure. It forces you to oversize your infrastructure, buying curated transformers just to handle the waste, and can lead to nuisance breaker trips caused by high peak currents. Mitigation solutions. To solve this, we cannot rely on standard capacitor banks alone. In fact, they can worsen the problem through resonance. We need targeted solutions. Active harmonic filters can inject anti-harmonics to cancel distortion, while tuned passive filters can trap specific frequencies. You must address the distortion to truly fix the power factor. Key takeaway: if you take one thing away from this session, remember this: to optimize modern power systems, looking at the phase angle is no longer enough. You must measure and mitigate total harmonic distortion to achieve a high true power factor. Q&A. Thank you for your attention. I'll now open the floor for any questions regarding harmonic mitigation or power factor calculations.